Hello everyone, my name is Pham Yatung. I come from the University Vietnam. Today I will introduce you about the lecture of soil erosion mapping using QGIS. This lecture belongs to climate change adaptation using digital geospatial screen and Earth observation. In this lecture, we will explore how to use QGIS to make a soil erosion map. And the content of this lecture are two topics. First, we will go to answer the question what is soil erosion, and the second one we apply QGIS to estimate soil erosion for a given research site in central Vietnam. So you see that the soil loss due to erosion is nowadays a global problem, especially affecting to natural resources and agriculture production. Some researchers calculate that the average rate of the soil erosion throughout the world are estimated between 12 to 15 tons per half per year, and the soil erosion are affected by wind and water. But the soil erosion under the water, under the rainfall, is the main cause for the tropical countries, especially in, for example, in Vietnam. Soil erosion have four forms. The first is flash erosion, sheet erosion, gully erosion, and ridge erosion. Uh, the gully erosion and ridge erosion is the main of the soil erosion formed in the mountain areas. Researchers have developed many tools to estimating the soil loss. We can apply soil and water assessment tool, or water erosion prediction projects, or the universal soil loss equation and its revised version. Among them, universal soil loss equation is widely used for study of the soil erosion by water because its simplicity despite some inconvenience due to its extensive requirement for input data. So in this lecture, I also use a universal soil loss equation to estimate the soil loss in a given areas of the central Vietnam. The universal soil loss equation proposed by Weismacher and Smith in 1978 and is applied in many areas worldwide and is described by the following equation. In this equation, A is average annual soil loss, R is rainfall erosivity, K is soil erodibility, LS is topographic factor, C is cropping management, and P is practical support factor. Now we will go through our 5 input data for universal soil loss equation. We go to the second part is how to mapping soil erosion. What we need the data. What kind of data we need? First, we need to a boundary of the water sets where we want to estimate the soil erosion. The second one, the rainfall data. We need some station, the data from some station within or around the watershed to calculate R maps based on the interpolation technique. We also need the dim data to calculate the topographic factor. We also need the soil type maps or soil organic carbon and soil texture map to assign or to calculate the K map. The cover map, this can be calculated from the NDVI map to create the C map, and a land use map or the survey data map to create the P map. So this is a 6 input data we need before to apply the universal soil loss equation to estimate the soil erosion for a given area. First, the rainfall run-up erosivity factor, we call the R. The R quantified is the effect and raindrop impact and reflect the amount and rate of the run-up associated with the rain. R factor was calculated based on the annual rainfall. For each region, they provide a linear equation between the rainfall and R based on the experimental research for many years. For example, here we can see for Indonesia, for Malaysia, for Honduras, for Italy, for US, or so on. For each for a specific area, they provide a equation to calculate the R from the annual rainfall. So in Vietnam, they normally apply two formula. The first, this one, and the second one is for this one. So because the difference between the this formula is because they apply for different research area. So because our research area is belong to Thừa Thiên Huế province, it's a center of Vietnam. So in my research, in this lecture, I will apply this formula. So first, we have to add the rainfall data. It could be in the Excel format, and it needs the information about the location, X and Y, and annual rainfall. And then we will apply the tool on the QGIS. The name is create point layer from the table, and we will plot as a point file here like this one. We have 1, 2, 3, 4, and 5. We have 5 stations around our research area. And then we go to the interpolation tool to interpolate rainfall map. In this research, I use inverse distances way method to interpolate rainfall map. And here we have the data files station, and we apply it to interpolation area. Then I use tool to cut the rainfall maps based on the boundaries of the research areas. And finally, we get a rainfall map for research site. Next steps, I use the tool disruptor calculator in QGIS and then apply the formula to calculate R based on the rainfall. This is the formula. And finally, we get the R map for this research site. We go to the slopes gradient factor. We call LS factor. LS factor represents a rate of the soil load under given condition to that at the site with a standard slope steepness of 9% and slope length of about 22 meters. Just steeper and longer of slope, the higher of the risk for soil erosion. And we see that here, for example, if the slope length is constant, is is no change, but slopes is change, is slope is degree, so LF factor also degree also. So more LS factor is mean less soil erosion. Sorry, less LS factor values is means less soil erosion. The LS factor relevant to the flow direction and flow the accumulation of the water. Here, for example, we have a flow direction. This one is show the direction it flows. And then here, based on the flow direction, they will calculate to the flow accumulation. And based on that's why we need the DIM data, digital elevation model, to calculate this LS factor. So now, how to calculate the LS factor? First, we have to load the DIM data and call the LS calculation tool. In QGIS, we have to go to the terrain analysis hierarchy and go to our factor here. We have to next step, we have to setting the parameter and then program and then export to the zip file. So what is parameter? We have to set up here. So that's easy. We just point to the dim data. We have to point out the output of the data of the LS factor here. Next, we go to the soil erodibility. We call K factor. The K factor is related to the crucial soil factor transgression soil erosion. For example, like organic matter content, soil texture, soil structure, or so on. We see that with different soil texture, we have a different K factor. So that's very important that we need a soil type map or soil texture map, or in case we don't have soil texture, we can to go to get a soil sample, and then we have to analyze on the laboratory to determine the uh, soil organic carbon or soil texture, and then we can apply the suitable formula to calculate the key. Here is just some methods to calculate the key value. For example, for this method, we can to use m. What's K is soil erosion factor, m is just texture from the first 15 centimeters of the soil surface, and OM is organic matter. OM is organic matter. S is mean the soil structure, cost, and P is the soil permeability. And for M, we can to apply this formula to calculate the M. And we also can to reference the previous research. They calculate the soil erodibility for each specific soil type. So to create a case map, we have to load the soil map. Most of them are the shapefile, and update the key value based on the methods that I uh, mentioned in the previous slide. And then we have to convert from the shapefile to the raster. So in this step, please notice on the pixel size and the field value. The pixel size need to be the same with the other input data like rainfall, like R map, like LS map, or other input data. And here is a step to convert the shapefile to raster. It can be done easy in the QGIS. And here's our key map with our research size. The 4 is the C factor. The C factor is the second most important factor that controls the soil erosion risk, and it reflects the effect of the cropping and management projecting on the soil erosion rate. Generally, the C factor ranks between 1 to 0. The C equal to 1 indicates no cover presence, and the surface is judgment as a bare land, where C near 0 indicates very strong cover effect and well-protected soil. To calculate the C in this research, I apply this formula. C equal to minus NDVI plus 1 and divided into NDVI is mean normalized differences vegetable index, and it can easy to calculate based on the satellite image by using this formula. This formula is near band minus to rest band and divide to the rest band plus to the near band. For example, in the Landsat A, the nearest band is band 5, rest band is band 4, and it depends on what kind of satellite image you will use, and you have to select the right uh, right band for this this formula. So to do that, to calculate the NDVI, first we have to load the red and near band of the satellite data. And here is a satellite, and here's for this one is satellite image, Landsat A, and here is our research site. And yes, again I use raster calculator to apply the formula to calculate NDVI as this formula, and here is we can typing or just pick this the file here to this dialog, this box, and just okay, and it will be calculate the NDVI. Then from the NDVI I apply this formula to calculate the C value. Then I will cut the C factor by the boundary phi, and here is our C map. You see here, you see for the the rest area here, this is mainly it's a river, so the river and stream there are no cover, but for this area, like this area is really very good in soil erosion protection, because their main area is most of them are the natural forest here for example, but for here this one is mainly is agriculture production like paddy rice, like the cassava or so on. So the last one we have to go to calculate the P factor, we call the support protective factor. The P factor is defined as the impact of the land use or the farming system on the soil erosion. So we have to term like a land use and farming system. The, the P factor adjusts the potential erosion by the water run up through the implementing the effect of contouring, strip cropping, and terrace contour farming. If there is no erosion control solution, then the p-value should be 1. P is the most uncertain value due to the difficulty in its estimation, so that we need to direct the observation at the specific land plot to determine the land use type and identify specific system. But it is very time intensive and costly. P-value can be derived from either image classification using the remote sensing data, previous study, or even expert knowledge. Some researchers suggest the p-value is rather than depend on the slope, but why others using the farming practice to calculate the p-value? So you see here is for this research, divided into two kinds, like paddyland, its p factor is 0, but for upland, if slope is from 0 to 2%, its p factor should be 0.6. But also the upland, but the slope is ranked from 2% to 7%, so the p factor should be 0.5. And for example, here they divide it in another way, like agriculture with slope 0 to 5% is the value of the p, it should be 0.1. But also agriculture, but if the slope is about 30 to 50, the p value should be 0.60, sorry, 0.25. So in this research, I apply the support practice factor in Assam Basin. This one is refers from a previous in South Korea, and here they also in combine of slope and land use. For example, in natural forest and grassland is p-value is 1 for every slope. But for plantation forest or industrial crop or so on, if slope is only from 0 to 5 degree, so the p factor should be 0.55. But if slope increase to 10 to 15 degrees, so the p value also increase to 0.90, and so on. So how to do this this map? First we have to load the land use map as a shape file and cut this file based on the boundary. And here is the land use map for whole province, whole district, and then I use the boundary of the watershed boundary here and just cut. And then we have a land use map of this area. We get the land use type map and update the land use type based on the select method to calculate the p-value, and then dispose based on the land use type field. We also need to, so for this, for last previous for previous slide, we already have a land use map, and now we already need to calculate the slope. We also need to use the dim, and then we have to calculate the slope map and then convert the slope map based on the threshold of the slope by the reclassified by the table. So because back to the previous slide, we have 0 to 5, 5 to 8, 8 to 10, 10 to 15, so on. So we have to reclassify by the table. And here is the step to convert the slope classification to shapefile, because we calculate the slope map, the output is a raster, so we need to convert to the shapefile because the land use map is a shapefile, and now we also need to combine between the land use type and slope together, so we have to convert into the shapefile the same format to make a combination. Here we have dissolved the slope classification based on the new value. And then we have to intersect the land use time map and slope map. Slope map now in the shape file, and then create a new view, and then we update the P factor based on the classification of the land use type and class and slope of the terrain. And then, because the R map, the LS map, the case map, and the C map are raster, so we have to convert the slope and land use type maps based on the P factor value into the raster, and finally we get the P map. It's very important thing. Now, easy. We just load on up the factor map like R, K, L, C, P, and then use the raster calculator to calculate the soil erosion rate. Here we have a soil erosion rate, and then we have to classification of the rate, soil loss rate for each pixel. And here, for example, we have 0.210 ton per hour per year, 10 to 50 ton per hour per year, 50 to 100 ton per hour per year in the yellow, and the red one is more than 100 ton per hour per year. For the soil erosion is really serious. So you can download the data that I apply in this research, this lecture. Uh, Follow the link here, or you can contact the lecturer or the member of this project to get the data. So thank you very much for the listening. I hope this lecture maybe is short and very simple, but will be uh, useful for you to make a soil erosion map for your research in the future. Thank you very much.